Hello?
Yeah, just let's say something into it.
Hello, can you hear? Okay, keep going. It's not changing at all.
No, it's not. How about this microphone master volume?
Okay, try that. Hello, hello. Is it getting louder? It is, yeah.
Okay. So I just did that.
Yeah, okay.
All right, let's get going for the afternoon session. So we'll be continuing our journey into effective field theories.
Okay, so let's start with any questions. Okay, so I was mentioning how we don't really need to worry too much, or you shouldn't worry too much about Lagrangian sorry, I forgot the face mask protocol. Lagrangian parameters, and an example of that is the modern scattering amplitude method, where you basically are looking at on-shell S-matrix elements and then iterating them to get loop diagrams and so on. And so the basic building blocks are the lower order on-shell amplitudes, and you don't ever have to talk about a Lagrangian at all. Okay, so in QED, for example, the basic parameters are, say, ME. Let's just call it, ME or M bar E, the running mass in the MS bar scheme, and the running alpha. So these are the Lagrangian parameters, but what's measured, the experimental inputs, are what's sometimes called the pole mass, which is the pole in the propagator. So if you look at the electron two-point function, there's a pole at p squared minus me pole squared, and that's the physical mass of the electron. If you had a bunch of electrons and you weighed them or whatever, you would figure what this pole mass is. And the other one is the potential goes like alpha over r at long distances. That's the Coulomb potential. And this is the alpha that's measured in atomic physics and everything else, which is 1 over 137.036. And then what you do is you calculate these two quantities from the QED Lagrangian. And you'll have a formula for ME pole in terms of the MS bar, et cetera. And then you use that to extract these MS bar masses. And then you can go calculate the Lamb shift or whatever else you need to. And in QCD, again, you have some running masses and a running coupling. But now there isn't an analog of the long-distance Coulomb potential at infinite distances or a pole mass, because quarks are not physical observables, and the coupling constant, the Coulomb potential, is not unobservable. And So what's done in non-perturbative lattice calculations or something is you adjust the parameters and get some physical quantities right. So for example, you could get the pion mass or the kaon mass and the proton mass, for example. I don't know what the most popular things are, sometimes the pion decay constant. And you determine the parameters of the Lagrangian through these non-perturbably, well, you calculate these compared to the PDG and then adjust your parameters to get these right. And then once you've fixed all your parameters, then you have predictions for everything else. And
What about the eta prime?
well, I mean, you can calculate everything, right? So, well, I can't, but some people in the audience can.
What's the problem?
Yeah, what's the problem?
I guess, is that fully predicted by just?
I mean, QCD, yeah. I mean, absolutely, yeah. I mean, and they have, I mean, now it's pretty amazing what the errors are on some of the calculations. Yeah, so when you can predict, the upsilon spectrum, the splittings and the levels. Yeah, yeah, there's no problem. I mean, this is why we believe QCD is right. There's no, everything which has been measured and everything which has been calculated agree to, as long as you put in the proper error estimates, there's no problem. Yeah, I mean, perturbation theory doesn't work for the eta prime, but on the lattice, you're not using perturbation theory. OK, so now here, I'm kind of thinking of QED as an effective theory in the sense that there are the weak interactions and everything else, which I'm not including. But nevertheless, so if I just call this LEFT for QED, the point I want to emphasize is that you can go ahead and calculate everything in QED, neglecting 1 over mw squared effects, starting with this QED effective Lagrangian. You do not need to know anything about the standard model, the weak interactions, G Fermi, nothing. It's self-consistent by itself. In other words, starting with a low-energy effective Lagrangian, you do not need to put in any other inputs than what are already there in the Lagrangian. Given the Lagrangian plus the renormalization scheme, you can go ahead and calculate in a systematic expansion. Now, one thing to remember is that the EFT is not, OK, so some of the words are that the low energy theory is sometimes is called the EFT. And if you happen to be in a situation where there's a high energy theory, like the standard model, which reduces to the EFT, then sometimes that's called the, sometimes people call it what's called the full theory in the sense that, oh, I was told to write bigger. Let's see if I can do that. In the sense that the QED EFT is given from the standard model that says the full theory by integrating out the W and the Z and blah, blah, blah. So these are just words people use, so you should know what they are. And we'll do an example of a matching later. So that's the other word which people use, which is matching. This is not always possible, but in cases where you can use perturbation theory, you can match from the full theory to the EFT. And what that means is you have, let's say, the standard model Lagrangian. You write down your low energy Lagrangian with arbitrary parameters, calculate some S matrix element in the 2, and make sure the EFT result agrees with the full theory result to whatever order in 1 over mw you're interested in, and then you can determine all the coefficients. So as I said, we'll do some of this, at least in some toy examples, explicitly. And then a couple of points which I mentioned already. The EFT and the full theory do not have to have the same degrees of freedom. So for example, QCD can match onto chiral perturbation theory, and you go from quarks and gluons to mesons and baryons. And even in theories like this, where you may have a vector potential, let's say, which was there in the standard model, or an electron field, which was there in the standard model. The electron field in the standard model is not, even though it's called the same letter, it's not the same as the electron field in the low energy effective theory. Because the electron field in the low energy effective theory includes various loop effects and so on in the full theory. And I'll mention this later when we do that, do an example. Now, so if I were to draw some kind of energy scale, so here's my low energy theory. I'm still writing small. Here's my high energy theory. By definition, the low energy theory is designed to get all the low energy experiments right, or S matrix elements right. So I can use low energy experiments and determine all of these parameters. So in QED, for example, okay, it's the long distance physics which is determining these. Now, often people say that, well, the low energy dynamics is insensitive to high energy parameters. That's true provided the input you have is also low energy input. And you can work only in here. But you could imagine a situation where you're given some high energy input. So an example of this is the top quark, for example. You could be given, the alpha electromagnetic, let's say, where if you were given alpha electromagnetic at some high scale, say at 200 GeV or something, the value of alpha electromagnetic in the low energy QED Lagrangian is going to depend on where the top quark mass is and other mass thresholds, because the matching between the two depends on these. So this idea that things are insensitive to high energy physics is true provided that the input is also determined from the low energy experiments. If you do experiments at high energy and then compare with the low energy EFT, there is going to be sensitivity to everything in between in the two theories. And the other thing I mentioned was that the degrees of freedom you have to use are not always obvious. So for example, in chiral perturbation theory, we went from quarks and gluons to mesons and baryons. Another example, which is kind of an interesting one, is in 1+1 dimension. There's a sine-Gordon model, which is a scalar theory, and there's a Thiering model, which depends on a fermion. And Coleman showed that they're, in fact, the same theory. And bound states of the Thiering model can be the scalar field of the sine-Gordon model, and solitons in the sine-Gordon model become the fermion of the Thiering model. So in this case, you have two different descriptions which look completely different, but they are actually the same. From four-dimensional point of view, when you do non-relativistic QCD, or soft collinear effective theory, it turns out you need multiple gluon fields to represent different momentum modes of the original gluon. I'm not going to discuss these. These are much more complicated than the other cases I will mention in the lectures.
I have a question.
Yeah.
So if you have multiple theories at low energy that are actually describing the same thing, do they have to have the same symmetries and number of degrees of freedom and things at those low energies?
OK, so the case I'm going to discuss, which is in 4 dimensions where some of this weird stuff doesn't happen, typically the mapping between the two is perturbation theory. So, so they would then have the same, the fields are called the same symbol. They're not exactly the same because you're making some field redefinition, but there's a mapping between the two. So I'll give one example where you can just do it and you can see what the connection is. Yeah.
So the sine-Gordon and Thiering duality requires massive versus massless, and I'm wondering if there's like a more general statement that could be made about things that are like this is not through perturbation theory.
No, this is not perturbative, and this is it's 1+1 dimensions is very special. So nobody, there's no real examples known in higher dimensions. The closest you could get to this is the Skirm model, where the Skirm soliton is supposed to be a baryon, but there's no real mapping between the two. Whereas here, I think Coleman had operator mappings, which show you how one operator in one theory translates into the other one.
Got it. Thank you.
So what exactly is the point you're trying to make by expressing that there's this duality with the two Lagrangians?
I'm saying that if you're given a theory, it's not always clear what fields you should use to describe the theory. That's all. So for example, here's a concrete example in 3+1 dimensions. When you're doing basically high energy QCD, you're using soft collinear effective theory. It turns out your effective theory has two different gluon fields. There's an AMU, which is, well, it's either ultra soft or soft. Let me not get into that. But there are two AMUs, one representing the soft modes and one representing the collinear modes. And in fact, originally, there was a proposal where one of the two modes was included, I think the soft, but not the collinear. And it turned out it doesn't match. The infrared physics did not match. And then people figured out you need two independent modes. So there are two different gluon fields in the effective theory, even though there was just one gluon originally in QCD. And then there's some issues with double counting and other things which have to be dealt with. But
in this example, so it doesn't matter what field you use, right?
sure, but you are given some spectrum, and you have to decide what to use, right? I mean, if you have just given experimental data, you have to now decide what theory to start with, right? If you're given the theory, then you don't care. Then you have it, right? But suppose you're just given some facts from some experimentalists found some bumps, and now you want to know what are you going to do. So then you have to figure out what variables to use to describe that.
Just because two descriptions are equivalent doesn't mean they're equally easy to use.
Yeah, that's right.
So you said this example, you have two different gluon fields.
Yeah.
And that's purely a trial and error statement, is it? A priori, can you know?
Yeah, so this is what I meant by you have to think. So what you're trying to describe in SCET is high energy QCD scattering, and the infrared physics you're trying to reproduce as collinear and soft divergences. You have to make sure that your EFT correctly produces the entire collinear and soft structure. Then it took some years to figure out that the way to do that was to have these two different fields.
Is there a particular perspective to take that might make looking for these kind of things easier? Because you have to think on it about it.
You got to think.
Okay.
I don't think you're going to avoid that.
No, but I mean, is there a kind of like, because out here you were talking about modeling specific aspects of
No, I'd like to say we're not modeling. You're trying to, as I said, you're trying to calculate in principle exactly, right, to arbitrary precision. It's very different from, let's say, the writing down a quark model or some fragmentation model or the Pythia Monte Carlo, which does something. That's a model.
But it seems like the number of gluon modes to include was a choice there.
No, it turns out it's because because the full theory by studying, there are these Landau equations which tell you what the infrared divergences are, and you look at those, and it turns out that you can prove that you have only these soft and collinear regions, and then turns out one gluon field doesn't do the job because they're very different momentum regions effectively. So in the EFT, they're like very different regions of phase space.
So every class of theories is a special case unto itself.
You gotta think. Yeah. Okay. Okay, so now let's start doing some more precise things. So first I want to start with dimensional analysis. I don't know, is this big enough or even bigger? Okay.
Even a little bigger.
Okay, let's try. It's hard. Okay, so the functional integral is some, I'll just use scalar fields as my notation, but it includes scalars, fermions, gauge fields, everything. Is some exponential of the action. And so the action, so I'm going to use square brackets to just denote dimensions, like whether it's mass, mass squared, mass cubed, et cetera. So the action has to be dimensionless because it's up in the exponent. So this whatever's up here has to be dimensionless. And the action is the integral in d space dimensions of a Lagrange density. So I'm going to be using little d for the space-time dimension. And I might as well say it here. I'll use capital D for the operator dimension. I'll have two dimensions. And so the Lagrange density has dimension little d because it has to it's compensated for by the x, which is dimension -1. I'm using the particle physics counting dimensions of energy with h bar and c is 1. So from this, because the kinetic energy for fermions has one derivative, and the kinetic energy for bosons has two derivatives, And they are terms in the Lagrangian, so they have to have dimension little d. You see right away that the dimension of a fermion field is d minus 1 over 2. The dimension of a boson field is d minus 2 over 2. And the gauge field, okay, so the space here is f mu nu squared, kinetic energy with a minus a quarter. And I guess if this is a real scalar field, there would be a half here. But again, this has two derivatives in it. And so a vector potential has dimension d minus 2 over 2. A covariant derivative or a normal derivative has dimension 1 because it's just 1 over x. So that always has dimension 1. And then if you write that this is the dimension of a little derivative plus ig a mu, then hopefully this can, g is 4 minus d over 2 is the dimension of the coupling constant. So in 4 dimensions, okay, which is what we want to work in, a scalar field has dimension 3/2. I'm sorry, a fermion field has dimension 3/2. A scalar field has dimension 1. A mu has dimension 1. Coupling constant has dimension 0. And now you can try and write down your Lagrangian as a series of operators starting with the lowest dimension and going up. And so this is capital D, the operator dimension. And if the dimension of the operator is 0, there's only one, which is the number 1, or a constant. And this is basically, we neglect it here, but it's the cosmological constant. It's a very important quantity. It's the coefficient of the operator 1.
Is it possible to have a field in the denominator of the equation?
Yeah, so this concept of locality also means that the Lagrangian is a polynomial. Essentially, we're going to be assuming the Lagrangian is some finite order polynomial in fields and derivatives. Because I wouldn't know what to do with a 1 over phi, for example.
So it's like assumption. Right?
If you want, it's an assumption or it's coming from locality. I mean, I've not seen any case where you would need one of those, yeah. So you could take it as an assumption. As I said, that we have no proof, so you can. Okay, then at d equals 1, all you can have is a phi. But usually you don't have this because you can shift phi by, you can shift phi to remove it. And often your theory has a phi goes to minus phi symmetry, and there are no such terms. So the first interesting one is phi squared at dimension 2, which is the scalar mass. And then you might try something like d mu phi, but okay, we're going to do a relativistic theory where this is not allowed by Lorentz invariance. So this isn't allowed in the action. Then you go to dimension 3, and you have a fermion mass term, psi bar psi. What?
I'm sorry, I just got confused. I thought the small d was the dimension.
It's the space, small d is the space-time dimension, and capital D is the operator dimension. So here, the scalar, right? So these I'm writing the operator dimensions. Okay. And then dimension 4, you have phi to the 4th, which is the lambda phi 4th coupling. You have Yukawa couplings, and then you have the gauge, these 3 kinetic energy terms, which I won't write down. But you can also have operators like phi, something like d squared phi, or some things like this, d squared phi phi. Now, because this is part of the action, there's an integral here, And so you can integrate by parts and write it as minus d mu phi d mu phi. So this isn't, so as long as you're doing functional integrals and actions, this is not an operator you need to include, because this is what you can call an integration by parts, IBP, an integration by parts relation. And it allows you to throw this one away and replace it instead by the other one. So
We're not collecting all operators of these dimensions, right? Total derivatives and stuff we're skipping.
that's what I mean. So the integration by parts means total derivatives are being skipped.
Okay.
But other than that, we're collecting all operators, which are Lorentz invariant, okay, because we're looking at the action. So everything which is Lorentz invariant and not a total derivative. Yeah. Oh, okay, I'll come back. Let me just come back to that in a second. Yeah, I was going to mention that. Is there anything else I wanted to say? Okay, so now if you are doing EFTs where you go beyond dimension 4, there will also be field redefinitions you can use to remove some of the operators, which I'll discuss when we get there. Okay, now in relation to his question, so for fermions, you can project a Dirac fermion field into psi left or psi right using a p left or p right projector, which is 1 minus or plus gamma 5 over 2 times. And in fact, you don't even have to have both components of the fermion. You could only have the left-handed field or the right-handed field. So then there's some additional, well, the field breaks up into 2, and in principle, the left-handed fields and the right-handed fields don't have to interact the same way, and that's, of course, what happens in the standard model, where the left-handed fields are weak interactions, and the right-handed fields do not. And so if you take E minus left, the left-handed electric field, this annihilates electron left, left-handed electrons, and it creates right-handed positrons. And the electron right field annihilates right-handed electrons, and it creates left-handed positrons. And if I were to have, let's say, positron left-handed, this would annihilate left-handed positrons and create right-handed electrons. I'm sorry, left-handed, wait, what did I do? Left and, yeah, electron right. And if you compare these two, what's annihilated by the E minus right is created by the E plus left. And so there's an you can use either of these fields. You can write the right-handed electric field as the left-handed positron field Hermitian conjugate, because then it swaps the annihilation and creation operators. And there's a gamma matrix here, which is the charge conjugation matrix. And if I use a dagger here, then this is I gamma 2. It just, I'll leave that from the field theory point of view. And so when you have a mass term like psi bar psi, if you put in the projectors, there are two terms. There's a psi bar left, psi right, and a psi bar right, psi left. But because a right-handed field can be written as the dagger of a left-handed field, this term can be written as psi left, and I can call this the charge conjugate field psi left. So for example, if this was the electron field, this would be the positron field. And I won't put in all the SC2 indices. So the electron mass term could be this. So you could write this as E bar left, E bar right, E left. But you could also write it as E minus left, E plus left, with the C matrix in the middle. Okay, it's two different ways of writing the same thing. And most of the time, this doesn't matter. But for neutrinos, it's kind of interesting, because you see, you can't have two E minus lefts, because that would violate charge by 2 units. But if you have a neutral field by the neutrino, you can have two new lefts producing a mass term. And that's the Majorana. This is called a Majorana mass. Forget the historical reasons why. But this violates lepton number by 2 units because it annihilates 2 neutrinos. And this is, we'll come back to this. This is an important point. So I don't want to go through all the subtleties, putting all the gamma matrix structure in here, but just remember that. So some people prefer to only use left-handed fermion fields. You can use some mixture of left and right-handed or whatever. But as far as the Lorentz group is concerned, the left and right-handed parts are independent of each other. So you can, and they don't have to have the same interactions. OK. So any questions so far? Yeah.
Does the operator dimension have to be integers?
So at least in 4 dimensions, so I should leave also here the derivative is 1. So you can see that the only place a half integer can come in is a fermion, but then Lorentz invariance, you need to have an even number of fermions. So then it automatically becomes integer dimension. This is sometimes called the naive dimension or whatever, the engineering dimension or whatever, because we'll see that there's anomalous dimensions. Due to interactions, what's called the scaling dimension of the operator can change. And so we'll briefly mention that. OK, so a Lagrangian then is we start writing down all of these operators, and we'll have a piece which is dimensions less than or equal to 4, which are basically everything I wrote down. So scalars and fermions with gauge interactions with their covariant derivatives, and possibly a Yukawa coupling and a 5/4 coupling. That's all you can have. And then if you're doing an EFT, in principle, you can have dimension 5 terms with 1 mass, dimension 6 with m squared, et cetera. These m's are playing the role of, for example, the scale A in the multipole expansion example. And these are down here just because the total dimension of the Lagrangian has to be dimension 4. So if you have a dimension 5 operator, it better have an m down below, some scale below, to make the net dimension of this term dimension 5. And if I look at amplitude, say from d this piece, or so like some 5/4 scattering amplitude, then the amplitude behave. Yeah.
Why do we want to make those higher dimensional pieces dimension 4? Why not make them like 3 or 2 or 1?
Oh, because just because the action has to be dimensionless, so the Lagrange density has to have dimension 4.
Oh.
You don't have any choice.
Sure, yes, never mind. Thanks.
Yeah. So if you look at some amplitude like this with n external particles, this will behave. Let's see, where am I? P, let me just call it p to the 4 minus the number of external legs. So here, E is number of external lines. So here, you have this amplitude would be lambda, and there are 4 external lines, and so that would be p to the 0. And if you have some more complicated amplitude like this with whatever, 1, 2, 6 external lines, it would go like 1 over p squared and so on. Basically 1 over p squared because there's a 1 over p squared from this propagator. Yeah.
Is this only true for scalars and gauge and bosons?
It's also true, you mean this 4 minus e?
Yeah.
It's also true for fermions if you include the spinner on the external line, because the spinner u kind of has a square root of energy in it.
Okay, I see.
Yeah.
Maybe I missed something, but is there a reason why we're not considering trilinear in phi
Oh,
terms? Are you
good
assuming
point.
some-
No, I can put in phi. My mistake. Let's put in phi cubed as well. Yeah. Yeah, so if you have a phi goes to minus phi symmetry, it won't be there in the standard model because of SU2 invariance is not there, but in general it's there. And in general, this phi field is also there, but then what you do is you shift by some constant to get rid of it, which is, OK. So from this term, you would get amplitudes which go like this. But if I have a dimension 5 operator, and I look at its contribution to, let's say, the scattering amplitude, then what you're going to get is, let's say, A5 is going like p to the 4 minus e. But now you have one more factor of the momentum over the mass. Because the dimension of the amplitude has to stay the same, and there's one factor of m here. And I should mention here, what I mean by p is any low scale. OK, so it could be the momentum. It could be p1 dot p2. It could be the mass of the light particle, because p squared is m squared, whatever. So anything with a low scale. And by low scale, I mean we have some EFT valid at some low scales, and then m is some high scale. So in the B quark example, this p could be mb or m charm or the light quark max, whatever, and then this would be mw. Yeah?
Can't you always get rid of the phi cube as well? Like through constants?
No, because you can do a shift in phi to get rid of the linear term, but now you can't do any more shifts. Yeah, I don't think you can. Yeah. OK. Now, if I had an insertion of one of these, the dimension 6, I would get a factor of p over m squared. Now, what happens if I have some diagram with 5 insertions of L5 and 3 insertions of L6 or whatever? Well, it's pretty easy to see that you're going to get an amplitude which goes like p to the 4 minus e plus some extra factor n, or p to the 4 minus e times p over big M to the n. And what is the value of this power? Well, you simply count how many m's you have in the denominator. And every m in the denominator has to have a p in the numerator by dimensional analysis. And every m in the denominator is given by the operator dimension minus 4. That is, 5 has a 1m, 6 has 2 m's, et cetera. So n is equal to the sum over all the vertices of big D minus little d, or in our case, sorry, let's di. The space-time dimension is the same for all, so it's di minus 4. OK? So this is, in some sense, trivial to see, because of every m, you can just see explicitly the m's. And the Lagrangian has no factors of big M in there. And what makes the EFT calculations non-trivial is we'll see that this formula holds even including loop diagrams. And there's no correction to it. So this is sometimes called manifest power counting. You can just count the m's by just reading it off. And loops preserve this power counting. OK. Now, when I'm doing this, OK, good. So let me I'm coming to exactly this point. So let's look at these terms. So if I were to do this power counting, I would say that, well, the d equals 2 term should be some, let's just write it this way. L2 should have an m squared in front of it. And then this is what you're saying. The L3 should have an m in front of it. And then L4 is fine. OK. So this is a very interesting point, because let's look at this one, for example. So now you have the operator here is the scalar operator. Now, suppose I put m squared there. OK, what does that tell you about the scalar? It's heavy. Its mass is the big scale. Okay? And okay, so by assumption, we're considering an EFT for the light dynamics. That's the starting point. So if phi is a field in the EFT, it can't have a mass m. If it had a mass m, we should erase it from my EFT. You see what I'm? So it can't be this. It has to be this times little m over big M squared, which is to say little m squared. Okay? Now, suppose I did this. Let's do the Fermion case. Psi bar psi, same argument. Okay? It has to be 1 little m over big M. Now, in terms of power counting, this is like 2 powers of what I was calling delta, the small scale over the big scale. And this is 1 power of small scale over the big scale. So effectively, it's converting what you thought was dimension 2 into, as far as the EFT power counting is concerned, it's converting it into an object which acts as though it has dimension 4, because its coefficient is small by 2 units. And the same thing for phi cubed. So it's not so obvious for phi cubed, but then what will happen is if you do a loop diagram with 2 phi cubed insertions, if each of these was m phi cubed, you would induce a mass for the scalar, which is big M. It can't have that. So you can only have little m times something of order little m times phi cubed. So it's kind of interesting that by construction, okay, so the starting point, remember, is we have some low energy theory, which means the fields in that theory have to be light, because otherwise they have no business being in the theory. And so even though I'm writing this as d less than or equal to 4, it's acting like it's acting like d equals 4. If you want. So you should sort of think of this all as d equals 4, because the dimension 2 terms have a suppression by 2, and the dimension 3 terms have a suppression by 1 extra power. Yeah?
I'm sorry, could you just repeat why it's acting like d equals 4?
Because it was a dimension 2 operator, but its coefficient is suppressed by 2 extra powers of little m over big M. So if I'm doing this kind of counting, I have to. So what am I doing here? I'm counting powers of the low scale over the high scale. So p over m is by p over m and little m over m, it's the same thing for me. All of them are light scales over big scales. So in doing this calculation, I'm saying, well, the powers of m are given by the dimension of the operator minus the space-time dimension. That's what I'm saying. So dimension, but that would tell me that this operator, the phi squared operator, should come with a big M squared. But it doesn't. It comes with a little m squared. And little m squared is big M squared times 2 factors of this. So it's effectively like shifting n, adding 2 more to n, which is to say, it's making d minus little d go, which was 2, it's going to make it 4. It's adding 2, that's and same everywhere. So every interaction in this part is acting, should be treated as having n equals 0, if you want. Yeah.
So I understand why to make the EFT work, we have to add the powers of little m over big M. But physics-wise, there's some reason we should think this is correct, that like the phi field should have a mass of little m rather than big M?
Well, yeah, so this is, what are you doing the EFT for, right? So if we have this EFT where we have a situation where there's a light scalar. Well, if the scalar is light, then its mass is light.
So it's like we've made some measurement to determine we have a light scalar, or we're creating a theory of a light scalar, therefore
we have a physical situation where there's a light scalar, and we want to write down some Lagrangian that describes it.
Okay, thank you.
Yeah. So you have some grand unified theory, and you have a Higgs, but the Higgs we know is 100 GeV. So it's clearly not 10, gut scale, 10 to the 15. So we know that, and we're writing down a theory for the Higgs. I mean, otherwise you would say that this, because there's the quantum gravity, the standard model can't exist because everything is at the Planck scale. Well, I mean, we know enough experimentally that that's completely false, right? So, yeah. So the input, there's some physics input, which is we are trying to describe a light scalar or a light fermion. Yeah. Okay, so OK, so this actually came up in some recent papers with Elizabeth Jenkins and Peter Stoffer, where we were like matching from the SMEFT to the low energy theory, and then you have to look at like Yukawa couplings and various things, and it turns out this makes the matching much easier because many interactions have additional suppressions, and you can throw them out. OK, so now let's go to a slightly more quantitative example, which is photon-photon scattering. So this is another famous theory. So Maxwell's equations are linear, and photons don't interact with each other. The waves just go through each other. But in QED, because of the box graph, you have nonlinear effects. And let's just say there's an electron here. So we're going to be looking at momenta much smaller than an electron. And OK, so we had some discussion in the morning. But this would it also requires that the electric field strengths and magnetic field strengths are much smaller than an electron squared. But OK, so the weak fields, low momentum. And what is my expansion parameter? Well, the low energy theory only has field strengths, F mu nu, because it's the photon. So the lowest order operator is just the kinetic energy term minus a quarter F mu nu squared. And then you can try writing down higher powers of F mu nu. That's all you have. Because of gauge invariance, you could try covariant derivative. But even though people write covariant derivative, it only makes sense when it acts on some field. So there's no like covariant derivative all by itself. So all you're left with is F mu nu squared. And if you assume charge conjugation and parity, which QED has, then the first operators you can write down. Let me write them this way, and I'll explain why. Alpha squared over me to the fourth, C1 F mu nu whole squared, plus C2 F mu nu F dual mu nu whole squared. Again, there are two F duals here, so it's again parity even. And these are two independent linear combinations you can get.
Sorry, the field requirement, I missed the discussion. Aren't you scattering around the vacuum? Or what's the field requirement? EP less than the mass.
We were this is, you missed the, if you have, we're looking at interactions of photons and things. So if you had external fields or something, you could have large field strengths. But from a particle physics point of view, if you're doing scattering, you don't have to worry about this. OK, and F mu nu has dimension 2. So these are dimension 8 operators, which is why you have an m electron to the fourth. And I'll discuss a little more about this later. But if you just estimate this diagram by saying that there are 4 powers of the electron charge from the 4 vertices, and a loop typically gives you, if you've done loop diagrams, a 1 over 16 pi squared from the loop, you get an alpha squared. So including that estimate, you would write something like this, where C1 and C2 are, you would expect to be some numbers of order 1. And the 4 pi counting, which I'll discuss later, is kind of important, because 16 pi squared in some sense is not that small. Okay, it's like 150 or something. So it's kind of useful to include that in the power counting. And so this is the famous Euler-Heisenberg-Lagrangian, where the C1s and C2s were calculated, and then plus dot, dot, dot. There can be higher order terms. So what is the photon-photon scattering amplitude? So this, what was the box diagram, if you want, you can think of this as the full theory diagram or the diagram in QED, turns into a diagram which just looks like this, a dot, or 2 dots, one for the C1 interaction and one for the C2 interaction. So what is the amplitude? Well, I get alpha, there's an explicit alpha squared over me to the fourth. And now each field strength has a derivative in it. So when I take this amplitude, there are 4 factors of the field strength, and we're going to get 4 factors of derivatives, or 4 powers of the frequency of the photons. And okay, to be careful, you'd have to figure out whether this was omega 1, 2, 3, whatever. But just generically, if these were photons of similar energy, or you were doing center of mass scattering, you'd get some 4 powers of the frequency. And therefore, the cross section, which is the amplitude squared times phase space, is, well, if I square this, I get alpha fourth over me to the 8, omega to the 8. And now phase space has to have the right dimensions to get an area, which is 1 over mass squared. So this is dimensionless. It's 8 powers of mass over 8 powers of mass. So you have to get a 1 over omega squared from phase space. And as I said, I would discuss some of the 4 pi counting later. But the rule for 2-body phase space is you put a 1 over 16 pi, not a pi squared, just 1 pi. And so this is alpha fourth omega to the 6 over 16 pi me to the 8. Let's okay, squiggle. This is a dimensional estimate. Now, imagine you didn't know about gauge invariance or photons, and I thought I could model this by some kind of scalar field. Then I would write an interaction Lagrangian, which was, well, a mu squared or phi fourth or whatever. Okay, 4 fields, not f mu nus. And then what you would find is that the amplitude here, well, this is dimension 4. So there is no 1 over me in the denominator. And the amplitude would go like 1. And the cross section would go like 1 over omega squared. Did I get this right? Yeah. And let's say you kept these alphas were the same, so you would get this alpha squared over 16 pi. But the factor of derivatives over me, the 4 factors of derivative over me are gone because I was estimating it and I didn't know about gauge invariance or whatever and estimated it incorrectly. Yeah?
Can we not write down a dimension 6 term also, like a F mu?
Yeah, so I'm assuming here charge conjugation plus parity plus. So yeah, so they could in principle be, we can, well, so then you have to have an even number of field strengths. But if you tried this operator, F mu nu, I'm not going to worry about up and down indices. F nu alpha, F alpha mu. Is this what you're worried about? Yeah. OK, this is 0. Can you tell me why? Yeah, each of these is antisymmetric. And so this is like a trace. If you think of F as a matrix, this is trace F cubed. Actually, this is an interesting point, so we might as well discuss it since you brought it up. Trace F cubed. But F is antisymmetric. So if you take the transpose of this, you'll get minus itself. But suppose I had 3 field strengths, OK? F1, F2, F3. This would be trace F1, F2, F3, treating each of them like a matrix. And each matrix is antisymmetric because swapping the mu and nu indices gives you a minus sign. So this is equal to the trace of this thing transpose, which is minus the trace of F3, F2, F1. And you will see that this interaction vanishes unless all the 3 Fs are different. And then you can have it. Yeah?
More phenomenological question. Do you know if it's practical to use this constraint the mass of mini charged particles to run this experiment?
That I don't know, because you mean you want light milli-charged particles running around a loop.
Right, but if you look at that, then
which one? This?
Sorry, probably the one on.
Yeah, this one, right? The cross section. Yeah.
The mini charged particle cannot be too
light. Yeah, because you would make.
Right.
Well, maybe you have a paper to write by the evening. But I don't know if people have looked at this. Yeah, but this is a constraint.
Okay.
Yeah, sure. You have to be a little bit careful if the frequency of the photon can actually pair produce milli-charged particles, but that might give you another constraint. But so here we're assuming that you can't pair produce E plus E minus. Okay, so back to what I was doing here. Okay, so the difference between these two is essentially, depending on which one you take in the numerator and which one in the denominator, is the mass of the electron over the mass of the frequency of the photon to the 8th power, okay? Because one has me to the 8th and the other one does not. And if you take optical photons, or say omega is 1 electron volt, the difference between the two is 48 orders of magnitude. Okay, it's not some tiny little thing. It's a huge difference in the cross section simply because of the ratio of ME and MA. So, and if I now compare with the exact answer, the second thing is broken. Okay. So this is a case where it's all been worked out, and I think even the next order term has been worked out. C1 is 1 over 90. C2 is 7 over 360. And the cross section is what we wrote down, alpha to the 4, omega to the 6 over 16 pi me to the 8 times, what is it, 15568, 10125. Okay. So we did pretty well with our dimensional analysis estimate. It took us 5 minutes or something, or less maybe, to get this number. Depending on how good you are, could take you, anywhere from maybe a few days to years. Okay, so it's a lot more work to get that. And the reason I'm mentioning it, and so clearly gauge invariance and counting the operators and so on plays a crucial role in this because that's what identified all the dimensions and everything to get the calculation right. But just doing this estimate is very useful before you start a project, because if somebody tells you, I have this dark matter model, I'm going to measure it, in 5 minutes you might find that your cross section is, either 48 orders of magnitude too big, in which case it's dead and ruled out, or maybe 48 orders of magnitude too small, in which case it's not worth doing the calculation because nobody's ever going to see it. And if it comes out in some interesting range, then okay, then you can spend the time and do the work. It's very, very fast and very efficient. Now, let's just compare a few other cross sections. So if I had a 5 to the 4th coupling, then that's basically the example I gave there. And the cross section goes like if I call this lambda 5/4, and I called it, whatever the coefficient there. But if I do lambda 5/4, this would be 16 pi omega squared. If I do chiral perturbation theory, then the leading interaction is two derivatives on pi squared. Yeah.
Is the omega there like the frequency of your scalar field?
Or the energy? Yeah.
Okay, sure.
Yeah, that's the same.
Thanks.
Mm-hmm.
I'm a bit lost as to where those came from.
These?
Yeah.
Hard calculations.
Oh.
Yeah.
No, you didn't look at the board and derive it.
No.
So the success of the dimensional analysis depends on that the coefficient is not too small. Do you have a probably reason to believe why C1 and C2 are not too small?
It's just no.
So if
it could be that this coefficient is 10 to the minus 8 or something. Okay. It's possible.
Then the dimensional analysis sort of
would fail. But there's no cases where that really happens. It'll fail, by 2s and 5s or something, but not by 5 orders of magnitude or anything. I mean, if it did, then you would have to really understand why the cross-section was suppressed so much. Yeah, but it's not a theorem that this number has to be between 1/2 and 2 or between 0.1 and 10. No. It just I mean, basically, you're using it to get this parametric form and saying there's some number of order 1 in front, but order 1 in a very loose sense. OK, but if you would, I mean, that difference there is 48 orders of magnitude. So you would, hard to imagine there's a 10 to the 48 somewhere in this diagram. OK, here you get, you get f to the 4th. This is the pion decay constant. So you square it in the amplitude. And then, again, it's omega squared to get the dimensions right. And if you did 4 fermion scattering, you would have an operator which was 4 fermion fields, which is dimension 6 over some m squared. The cross-section would be, again, just there's a 1 over m squared here in the amplitude. You square it, you get an m to the 4th in the cross-section. And so you have to have 2 powers of omega upstairs. And if you did scalar fermion scattering, so this is a psi psi to psi psi. And if you did psi phi to psi phi, your operator could be psi psi phi phi, which is dimension 5, 5 over 1m. And the cross-section is 1 over 16 pi m squared. And now that has the right dimensions. OK, so I mean, you can see it didn't take very long to estimate all of these. And they're quite different. Well, these two are the same, but otherwise they're different energy dependencies and dependencies on the new physics scale. OK, any questions? Yeah.
I'm a little bit confused. Massless kinematics on the in and the out state stack.
I'm just doing an estimate where, so this omega could be the energy.
Yeah, but I'm worried about the top line there, the 1 over omega squared. There's an assumption about kinematics.
Yes, that. I mean, it could be m squared. Is that what you were? It's like 1 over s.
Yeah, okay.
Yeah, so I'm saying that s and m squared and stuff are all the same for. Yeah. So we could imagine you had some m's which are order MeV, and then the high scale is of order MW, let's say. And then whether it's MeV or 10 MeV, whatever, I don't care. What I'm really calculating is the ratio, the dependence of. Basically, this is big M to the 0. This is big M to the 4th. F is like the new high scale, big M to the 4th and big M squared. That's really what's being tracked. Yeah.
When you do these estimates for the fermions, like with external fermion states, do you need to worry about that? Like having like you get an extra factor of mass if you have like an external fermion, right? An imperator. You have like an imperator output.
From where?
So if you have like an external fermion line,
yeah.
All those extra factors on the external fermion lines.
You mean from the spinners?
Yeah.
Yeah, that was what I was mentioning over there about how it. I don't know if it's still there. It cancels out. Yeah, so it doesn't matter because what you're really doing is you're counting the big scale, which is in the denominator. And now dimensional analysis tells you whatever's on top had better compensate for that.
So the only thing you're just using in the numerator is dimensional analysis. You're not worried about.
They're all the same because, I mean, so for a spinner, I mean, I think this is related. So U bar gamma mu U is twice the momentum of the external line, right? So effectively, U has dimensions is square root of 2e in some sense or 2 omega in my notation. So, OK, let's do this one, right? So the operator had 1 over m squared. So the amplitude is 1 over m squared. So the cross-section is 1 over m fourth. I didn't explain, but it doesn't matter. There's a 16 pi because it's two-body. Don't worry about it. It has to have the dimensions of cross-section, which is 1 over a mass squared. So it has to have 2 powers of something on top. And it's a low scale.
I think I understand the process. I just wanted to make sure that having the direct spinners is not going to mess up anything.
It doesn't mess up anything because it's just dimensional analysis. And it's also related to Tom's question. I don't care whether this this omega is, S or T or M squared or whatever. All of these for me are the same size. Yeah, that's right. So it doesn't change anything. Hold on. OK, I'll let him start, and then you next. Yeah.
Does it change if you have a third scale? Like suppose your mass of your fermion is very much smaller than your omega. And then when you do this estimate, you can't just say instead of mass.
Yeah, so we're dealing with two-scale theories where there's some high scale integrated out and then some low scale. If you have multiple low scales, then you can actually repeat the EFT process of going. So, OK, so here's you have MW, you have MB, and you have M electron or something, right? So you can first go to an EFT where you get rid of MW, and then you can go to another EFT where you get rid of MB, and then, OK, so we're just doing a simple two-scale example, but there are many examples with multi-scales, and then you do one scale at a time, and you can solve the problem. 1 second, let's, yeah.
This is maybe too specific, but for the light scattering, I was kind of expecting that there's some log of ME over omega. Is there some simple reason to see why there are no logs here?
Yeah, the reason is that the gauge invariance tells you that you have to have it has to be F mu nus, not A's to the fourth. So you have to have 4 powers of external momentum. And this integral was log divergent. It's a 4 Fermion propagator, so it goes like d4k over k to the fourth. But now the fact that you've pulled out 4 external momentum means it effectively goes like k to the 8 and is convergent. Which is why Heisenberg could calculate it, because they didn't know about renormalization and stuff. Yeah?
For the 5-fold, is the sigma is higher divergent? For the 5-fold theory, is the sigma is higher divergent?
I mean, at low omegas, right? Yeah, that's OK. Yeah. No, that's what's Tom's question. So they're all the same scale, right? So if you now have a massive scalar, then you got to put in whatever the what is the details of what this omega squared actually is. It's something of dimensions of the light scale squared. And for me, I'm not worrying about that here. So we're just doing these estimates. I mean, to really get the cross section, I mean, there's a lot of work you have to now do. But the point is you've gotten rid of the high scale. And I'll write down the B physics example, and you'll see what happens. But yeah, so for me, I don't care what is meant by this omega right now.
It's like morally a moment.
Yeah, because mass squared is p. I mean, m squared is p squared, right? OK. Now, OK, so now if you go back to the standard model and assume that at least the field content is and the group is correct, that is, we have an SU3 cross SU2 cross U1 gauge theory with the standard quantum numbers that everybody writes down with a standard Higgs doublet, which is an SU2 doublet. Then you write down all possible terms up to dimension 4. And that, by definition, is the standard model. And Sally wrote this down in the morning. Now, you could imagine that the standard model is actually some kind of EFT, and there's some new physics. And this originally, Weinberg did this, and I think Wilczek and Z. There's some gut physics or whatever. So what higher dimension operators can you have? So you can start with this and write down higher dimension operators. And the first one you get, OK, so what do we want? We want the standard model fields. And we need Lorentz invariance and gauge invariance. And the first operator you can write down is dimension 5. and it has the structure. So I won't write down all the indices, but it's Higgs field, lepton doublet, Higgs field, lepton doublet, 2 factors. Yeah.
So I see in all of your examples, our first step sort of is to write down these higher dimensional operators. I don't think I'm appreciating the direct connection between writing down those higher dimensional operators and then moving to an EFT.
That is the EFT.
Okay.
Because, so here, what are we doing? We're saying there's some new physics. I don't know what it is. I don't even know what scale it's coming from. All I'm assuming is it's at some scale which is large compared to MWMZ VEV, 250 GeV. And since we're physicists, large means 2 times as big, maybe 3 times as big. That's large. Because you typically get squares, so if it's 3 times as large, you get 10% corrections. So to 10%, the standard model would be accurate. So what we're doing here is, this is these L5, L6, et cetera. And I don't know what capital M is or whatever, but okay, when Weinberg and people tried to write this down, they were assuming it was some gut, and then the M there would be some gut scale. But so today what people do is write down what they call an SMEFT, where you don't know what big M is, and you just put it into the coefficient C in front, and you fit and see whether you find a deviation. And really, you don't need to get too excited until one of these coefficients is reliably not 0. So as long as it's limits, it doesn't really matter.
Sorry, so this assumption of these gauges persisting through the higher theory as well, is that a very particular choice, or is that something that has to be true? Because we do see like symmetries in effective terms that don't show up in full description.
No, but we're writing the effective theory down. And we're assuming the effective theory has SU3 cross SU2 cross U1 gauge invariance.
But that is particularly an assumption, right? Like that's not, we could have written it with small terms breaking.
Well, I mean, there's like a lot of experiments which tell you that you can't do that. I mean, the entire standard model, I mean, the whole structure of the standard model would break. I mean, you can't just break gauge invariance. The whole theory would completely collapse.
Right, but I mean, what if it, like, even if we go to like dimension 50 or something, even so we guarantee that we cannot write anything that violates these?
Well, I think,
or we should not.
I mean, you could have, you could also say the same thing about Lorentz invariance, right? There could be some dimension 50 operator which violates dimension Lorentz invariance. But what we do know is that to very high accuracy, I don't even know how to start by calculating in a theory without SU2 cross U1 invariance, gauge invariance, because you have dynamical W's and Z's. And so I think that's a pretty safe assumption at this point. Yeah.
You say standard model fields, you made the comment before that the field is not the same.
So all I mean here is quantum numbers. So that's all I'm talking about.
But in the photon example, is there a way to say that when I keep the electron and when I have the EFT, the A field is different?
Yeah, so I'll do one example of a decoupling, and I'll mention it in that example, and it should be clear what happens and everything else. Yes. Okay, so there's some M here. I could call this M, whatever, M. So this is sometimes called the Weinberg operator, but anyway, so it's 2 lepton doublets, so this operator is delta L equals 2. And when the Higgs field gets a VEV, this reduces to the 2 Higgses give you 2 VEVs over M, and then you get a neutrino, because the index of the component of the Higgs which gets a VEV is coupled here to the neutrino part. The lepton doublet is neutrino electron, and okay, this is a nu, and the Higgs field VEV is 0 V over root 2. And this invariant, I said I wouldn't write it down, but basically HL, if you put in SU2 indices, is HI, LJ, epsilon, IJ. And so this neutrino couples to the V over root 2. And so there's some 2's here, but this gives you a nu left, related to the earlier comments about Majorana masses. So this produces a neutrino mass, which is Majorana. violates lepton number by 2 units and is of order the Webb squared over m over m. So this is sometimes called the seesaw mechanism, that if you have some high scale big M, you get a neutrino mass inversely proportional to the high scale. And what I put in some numbers, if I took this to be 246 GeV, and I put this to be, what was it, 10 to the minus 2 electron volts, then this M turned out to be 6 × 10⁻15 GeV. And now you could argue whether I should have the Webb squared here, or maybe I should have a factor of the Yukawa coupling, and this should be m tau squared or me squared or whatever. But m is some high scale. It's not the weak scale for sure. But I think the most important thing about this, if these ideas are correct, is that the neutrino mass should violate lepton number by 2 units. Okay, that's the operator that you have. And so neutrino-less double beta decay, which is looking for this, is a very important thing to do, because it'll test whether the neutrino mass is delta L equals 2 or not. And let me just finish this. The other one, which was if you go to dimension 6, so that we end the story, if you go to dimension 6, there's an baryon number violating operator, which is 3 quark fields and a lepton field over m squared, which is a delta B equals delta L equals 1 operator. And so again, baryon and lepton number are in the standard model what are called accidental symmetries. That is, we don't impose them on the standard model. We write down the most general possible Lagrangian consistent with gauge invariance. And it turns out that all the operators conserve baryon and lepton number. And the first one which violates lepton number is dimension 5. The first one which violates baryon number is dimension 6. And from this, you can see that the proton, well, the decay width of the proton should go like m proton over 16 pi. That's has the correct dimensions to be a decay rate. But then this m squared gives me an extra m proton over m to the 4th suppression. And just to put in numbers. So this tells you the lifetime of the proton, which is 1 over gamma, is 10 to the 30 years times m over 10 to the 15 GeV to the 4th power. So you naturally get a very long-lived proton. And if baryon number had been first at dimension 5, not at dimension 6, you would lose 2 powers of this m suppression. You would lose 30 orders of magnitude relative to the 10 to the 15 GeV, 2 factors of that. And the proton lifetime would be 1 year. Okay, so it's kind of nice that in the standard model, the numbers are kind of working out to be something sensible. And if you tried new physics, which sort of couples to color and weak interactions in some non-trivial way, you will get dimension 5 baryon number violation. It happens in SUSY unless you impose some R symmetries to forbid the operators. And those would be completely ruled out, obviously. OK, so I think this is a good place to stop. Since time's up, right? Yeah, OK.
There's no 4th lecture today, so there are